Sequential switching in first order transient circuit happens whenever there's more than one switching event that happens in the circuit. And this can be, well, I have one switch in position A, we move it maybe to position B, and later on we'll change it back to position A. So this will be multiple switching. Or maybe what happens, I have a switch that is in position A, we move it to position B, and then we have another third position for the same switch at C. They don't happen all at the same time, but they happen in sequence. And sometimes what we do is we have a few switches, actually, maybe one in here that goes from A to B and another one that goes basically from C to D or something like that in sequence. They don't happen both at the same time. So in that case, well, it's still a first order circuit, so what we can do is we can use the general solution to find it. However, what happens is we have to pay a little bit more attention to what T0 is, because T0 becomes 0 for the very first switching, and maybe after 40 milliseconds, this is what I did in here, so that T0 becomes 40 milliseconds. So the initial condition will definitely change between the different switching. The key thing to actually solve sequential switching circuits is to draw the circuit at different stages, right before the first switch, then right after that first switch, and then right before the second switch, and so forth. And I think the easiest thing to do is just to give you an example so that we can, so I can show you how this works. So in this example, we are given a circuit that contains one inductor, which is one storage element. So it's a first order circuit. And since the source in here is DC, so it's a first order transient circuit. And what happens in that particular circuit is we have one switch in here and the second switch in here. So the switches have been closed for a very long time, and at time equals T0, what we do is we open the very first switch in here, so we're left with this part of the circuit in here. And you wait for 35 milliseconds, and the second switch actually opens, and basically you end up with this particular circuit in here only. And what we're interested in is to figure out the current flowing through this inductor. So in sequential switching, again, initial values, the initial value for the inductor current or the voltage across the capacitor matters. And of course, if we target something that doesn't change right before switching, right after switching, our life becomes easier. And in this particular case, that's what I'm doing in here. I'm just basically looking at something that doesn't change instantaneously, which is the current through an inductor. All right, so the key to solving sequential circuits is to draw the circuit at different stages. So the very first thing we're going to do is I'm going to write the equation that describes them, which is the general solution for differential equations. And that tells me that whether it's I or T or V, x of t is just simply the x final plus x at t0, not necessarily 0, at t0 minus the x final e to the negative t minus t0 divided by tau. And again, T0 doesn't have to be 0. So in here, it will be the very first one will be 0, but the second one will be 35 milliseconds, and we'll see it now. So of course, in this particular exercise, what we're doing is we're targeting IL of t. That's what we're after. So what we will do is we'll figure out the IL final, and then we'll figure out the IL at T0 initially, and then at T35 minus, I will say IL final, e to the negative t minus, I'll keep it at T0, and this is tau in here. Okay, so what do we need to do? Well, we need to figure out the initial condition and the final condition and then tau. Okay, so I will do that, and I'll start basically by finding the initial condition. So finding the initial condition. Condition at exactly T0 equals 0. And what I will do is initially I'll basically take a look at that circuit at exactly right before switching. So I'll take a look at it at T0 equals 0 minus, basically at T, not necessarily T0, let me just say at T0 equals 0 minus. So of course, in that particular case, the switches have been closed for a very long time. So this particular inductor here happened to be now just simply a wire, and I can draw it like a wire in here because it's a short circuit. That's what we have. Now, of course, because this one here is a wire at this point, that means the voltage across this resistor is 0. Okay, and if the voltage across it is 0, there's no current flowing through it. So technically speaking, I can go ahead in here and just remove this particular branch in here because nothing is happening in that part of the circuit at that particular moment. So now, again, what we're after is not this IL. This actually will be IL exactly at 0 minus, which is the same to say it's IL exactly at 0 plus after we actually just open the switch because the current doesn't change. And that's what we're after. What we need to do is we need to analyze this circuit so that we can figure out what this IL of 0 is, or just basically what's the current flowing through the 3 ohm resistor in here. There's multiple ways to do this. I think maybe one of the simplest is to do a source transformation on this one here. So let me just do that. We do source transformation and then we'll end up with a bunch of resistors in parallel. So the source transformation will tell me this one here will be a source in parallel with the 4 ohms. Okay, and then the 12 ohms stay. Okay, and of course we have another 6 ohms in here. Okay, and then what we have in here is basically 3 ohms. And what we're after is actually the current going through this one here, just so that I don't lose it. It's the same current here. That's what I'm after. Okay, and of course we need to figure out what the value of this current is. The value of this current is simply 60 divided by 4, and that basically is 15 amps, I would say. Yes, because everything is in ohms, so this is just simply 15 amps. All right, so now what we're after is the following. We're after IL of 0. I'm just going to call it 0 minus for now, but you should know that it's the same as 0. So what we happen here is we have 1, 2, 3, 4 resistors in parallel, and we have a source in here. We can just use current division to find what this current here is. And just as a quick reminder, the rule for current division tells me that you need the source. Basically I source in here, let me just call it IS, let me just write it in here so that you remember it. So if you're interested in some sort of an IJ, which is like I1, 2, 3, whatever it is, what you do is you do basically I source multiplied by the R equivalent of these parallel resistors divided by RJ, which is in our case is that 3. So what we need is our source is basically 15 amps, and we'll multiply it by R equivalent, which is just simply the 4 in parallel with the 12 in parallel with the 6 in parallel with the 3 divided by 3, and that will give us that value, which is exactly 6 amps. Okay, so figure out the initial condition. That means IL of 0, so let me just highlight it in here. So IL of 0 minus, which is the same as IL of 0 plus, right after this switch opens in here, it's going to be the same. And that becomes in here, which is IL0 is just simply 6 amps. That's what we have. So let me just highlight it so that we can get back to it. All right. So we found the initial condition. So now what do? Well, we need to find, well, because in this particular case, the initial condition right before switching and right after switching is the same. So we don't have to worry about the T0 plus. So what we can do is now we can go ahead and just find the final condition. Okay, so finding the final values. Okay, so the final condition. And by final, here's the deal. Let me just draw that circuit in here. Let me just show you the circuit. So what happens in here is at t equals 0, what we do is the following. At t, and let me just do this here. We'll highlight that. So what we did is we opened this particular part of the circuit. By opening this part of the circuit, what happens now, this is what we're left with. So for final condition for the very first switching, even though I know after 35 milliseconds I'm going to open another switch, I'll ignore this for now. And what I will do is I'll take a look at whatever is left in the circuit, and I'm going to say, well, what if we waited forever in that particular state and that switch 2 is closed? So that's the final condition I'm after. Okay, and of course in that particular case, well, I do not care about this part of the circuit in here, okay, because now it's not part of where the inductor is. So that's what I'm left with. And what I'm after is the following. I'm after this current in here, and in this particular current as well, just as a reminder, well, if you wait for a very long time, this inductor will also be a wire. So that's what we have in here. So we'll draw that as a wire. Okay, and what we're after is this one here, and I'm going to call it IL final. Okay, and we can call it IL final 0 because there will be another final in a few moments. So that's the current that we're after. Okay, and if you think about it in here, well, there are no sources anyway, so it's very simple to say that the final value, okay, I'm going to call it that, is just simply 0, and that's it, because there are no sources whatsoever. That's basically the reason why. So there's no sources, so that's the final value. All right, so what's left now? Well, we need to find the time constraint, okay, and that would be here. Sorry, the time constant, not the time constraint, constant. Okay, and that is just simply tau equals L divided by R in this particular case. And again, this is, I'm just going to call it tau 0 because we'll have different time constants. So what we do is, again, I'm just going to draw that circuit in here. Okay, so we're going to do this here. So what we have is the following. I'll just basically do this here. Well, after we open that switch in here, we'll open that switch. So this part of the circuit is no longer relevant. And what we're interested in is the point in here. So I'm interested in the Thevenin equivalent for the circuit from this perspective in here. Okay, and really what I'm after is actually the R Thevenin that we can see from here. V Thevenin, by the way, will be 0 in this particular case because there are no sources. But anyway, so what we're after is R Thevenin, or the R seen by the inductor in from here. Okay, not necessarily R Thevenin, but basically R equivalent in here, because this is basically the resistor seen by the inductor. So that's what we do, and that simple becomes R equivalent, and I'm going to call it equivalent 0 because it's the first one. It will be just simply 3 plus 6 in parallel with the 18, and that number would be 6 ohms. All right, so R, well, that's not what we're looking for. We're looking for tau, which is simply L divided by R equivalent 0. Okay, and what we do is, let me just see, the value of L is 150 millihenries. So 150 times 10 to the negative 3 divided by 6, and that equals to 1 divided by 40 seconds. That means 1 divided by tau is just simply 40 seconds to the negative 1. Okay, so that's here is what we're looking for. All right. So I believe we have everything we need to do in order for us to figure out what the IL of t, well, if t is right after 0 and right before switching at 35 milliseconds. Okay, and that becomes the following. So what we need to do is we need to take all of these equations and we just basically substitute it. So I'll just basically copy this here just so that you can see it. Okay, and we'll put it right here. That's what we need. So what we need is the following. We need IL of t. This is again for that particular case, which is between 0 to 35 milliseconds, right before we actually open the second switch. So what we have is the following now. IL of t is just simply IL final. I think this here should be positive. I didn't put positive in here. There should be positive. Okay, so put ILF positive in here, and that will become, well, what's the final here? Well, the final in this particular case is 0 plus what's the initial? The initial is at 0 at this point, which is 6 amps, minus 0, e to the negative t. In this particular case, t0 is 0 divided by tau. Well, I know that 1 divided by tau is just simply 40. Okay, so that basically IL of t is just simply 6 times e to the negative 40 t, and that's exactly amps, and that's for t is between 0 and 35 milliseconds. So that's what we have in here, and let me just highlight it. Okay, so that's basically between 0 to 35 milliseconds. Now, the circuit, if you take a look at it, because we have if we didn't have sequential switching, we'll be done. But now, when in sequential switching, what we have is we have another switch here that opens at 35 milliseconds, and now we're interested in whatever is left in the circuit. So what we have now is the following. We have now a circuit that looks something like this. So let me just do this. So here's the circuit, the original circuit that we have, and what we said is, well, at T0 we open that switch in here. So what happens is, like, we eliminated this part of the circuit. And now this is what we're left with. And now at T equals 35 milliseconds, what we did is we opened that circuit. So what we need to do is actually it's the same type of analysis that we've done before. So IL of T will be just simply the same exact equation, IL, but now the second final, I'm going to call it ILF1. Okay, plus IL, when now the T0 is just simply 35 minus IL of final 1 e to the negative t minus, this time it's 35 milliseconds. Okay, we can of course just basically substitute this millisecond by its whatever value we need. For example, this one here is 10 to the negative 35 or something like that. Negative 3 because millisecond divided by tau. So I'm assuming that tau will be something in seconds. That's why I multiply by 10 to the negative 3. But anyway, the idea here is what T0 now becomes 35, not 0. Okay, so what we need to do is we need to figure out this value, and we need to figure out this value and the tau as well. This is a different tau as well. So let me just call this one here T1, a tau 1, for example, because it's a different tau. All right, so let's, again, we find the initial. Okay, so finding initial value. Okay, so the finding initial value, well, initial here is at t is at 35 minus Okay, that's what we have. Like not 0, it's right before this switch happens. And we can simply, because we're targeting the current across the inductor or flowing through the inductor, that means right before 35, right after 35 is the same. So what we can do is we can actually use this equation to find it. All right, so what we have is, well, let's figure out what's IL of 35, exactly 35, which is 35 minus, 35 plus, or 35. It will become 60 e to the negative 40. Well, the t should be 35 times 10 to the negative 3, because this is how we dealt with that, because we dealt with the 40 to be second minus 1, if you remember in here. Okay, so because it's second minus 1, that's what we have. Of course, we can just fix this one here just to make sure that you guys can see it in here. That should be 10 to the negative 3 in here. All right, so what is that then? Well, that will be simply 6 times e to the negative 1.4, and that's it, to the negative 1.4. That's what it is. So we multiply 6 times e to the negative 1.4, and that answer will be 1.4. I mean, I'm going to approximate it, about 1.48 amps in this particular case. All right, so that's basically the initial at 35 milliseconds. All right, 1.48, that's the initial value that is flowing through this here. So what happens now is we need to find the final, and the way we find the final is here. So let's do that. Okay, find ending now the second final condition, not the original one. Okay, and that's basically when t goes to infinity. Okay, and what we have is, this is the original circuit in here. What we have is we're going to eliminate the first part, which is here, because we opened it at t equal 0. And of course, at t equal 35, what we did is we eliminated that. That means we eliminated this part of the circuit too. Okay, so that's what we're left with. We're left with pretty much just an inductor. And of course, we know the inductor at infinity in here. What happens is the following. We have an inductor that will be replaced by a wire. And what we're after is this one here. We're going to call it IL of F. Let's call it 1. And of course, hopefully you can see it now. IL of F1 is just simply 0, because if we wait for a very long time, there are no sources. That's pretty much it. So it's 0 in here. So that's here. Let me just highlight it. This is the initial one in here. Okay. And this is basically the final. So what's left? Well, what we need to do is we need to find the time constant. And now finding the second time constant, tau 1, which is basically, I'm going to call it, again, it's L divided by R1 in this particular case. So what is this R1? Well, I have an inductor connected to 3, connected to 6 in here. Okay, and what I'm interested in is the R equivalent that that inductor can see. And in that particular case, the R equivalent is just simply 3 plus 6, which is just simply 9 ohms. That means tau 1 is just simply, I believe it's 150 millihenries divided by 9, and that equals to 1 divided by 60 seconds. And of course, 1 divided by tau 1 is just simply 60 second minus 1. And I think we have everything we need to actually write the equation for when t is greater than 35. So let me just do that. So what we have is the following. Let me just copy this equation. Okay, so this is the equation that we need. And all I have to do is just substitute it in here. So we do that. Okay. So what we have is the following. So no, this is IL. So for t is greater than or equal to 35 milliseconds. Okay, what we have is IL of t is just simply, well, what's the final value? We decided that the final value should be 0 plus what's the initial value. We computed the initial value to be 1.48 approximately, 1.48 amp minus 0 e to the negative. Well, this will be, I believe, this will be 60 times t minus 35 times 10 to the negative 3. Of course, the t in here should be in seconds because this is also in seconds. And we clean this here, and we have IL of t is just simply 1.48 e to the negative 60 t minus 35 times 10 to the negative 3. And that's basically in amp, and that's for t is exactly greater than or equal to 35 milliseconds. So that's basically the second one here. All right, so that's what we have. Of course, we can combine these two. Let me just write this for you. And here's basically the equation that describes it. So IL of t for this particular inductor is just simply when t is between 0 to 35 milliseconds. This is the equation that describes it. Just make sure that t is in seconds actually. And the same thing goes when t is greater than 35 milliseconds. You just basically substitute whatever the value of t in seconds in here, and you'll get that value. You can, of course, go ahead and plot this and just sketch it to figure out how the current changes with time.